Hello everyone, this video is the second lecture on integrated circuit board design technology. The content of this lecture mainly introduces some basic layers that we use when designing layouts, as well as some circuit failure mechanisms that we need to pay attention to during the design process. First, let's look at the first part, which is the basic layout layers. The most commonly used layout layer is the metal layer is the most commonly used layer. Its main function is interconnection, allowing us to connect basic circuit components like transistors, capacitors, and resistors. Typically, an integrated circuit process provides several layers of metal lines. For example, as we mentioned before, the EP4M has 4 metal layers which can serve as interconnections. These 4 metal layers are at different heights, and there is no electrical connection between different layers of metal. To connect them, we need something called a via. In CMOS processes, the material for these metal lines is usually aluminum or copper. Generally, in processes with thicker lines, aluminum is used, while in advanced processes, like those below 90 nanometers, copper is typically used. After we draw a basic metal line in the layout, the actual processed line has a certain thickness. For instance, in a 180 nanometer process, this thickness is about 0.5 micrometers. This thickness of the metal layer is what we refer to as a metal interconnect line. Within this metal interconnect line, there will be parasitic capacitance and resistance. Why do we have capacitance? As we discussed earlier, the metal line forms a parallel plate capacitor structure with surrounding metal lines, whether it's the sidewalls or the surface, leading to parasitic capacitance. Additionally, since it's made of metal, it inherently has resistance, which contributes to parasitic resistance. With parasitic capacitance and resistance, our metal line is no longer an ideal conductor, as we might assume in our schematic design, where nodes have no parasitic resistance or capacitance. In reality, once the layout is processed, it carries these parasitic properties. So if we use this metal line to transmit a signal, for example, a digital control signal or a clock signal, the signal that comes out at the end of the metal line may look like a red line, indicating that it has a certain delay compared to the input signal. This means that the parasitic resistance and capacitance can cause signal dispersion. What does this mean? It means that due to the presence of resistance and capacitance, the metal line responds to different frequency components of the signal at different speeds. Overall, the output signal will experience a delay. How much delay are we talking about? We typically calculate this delay using a distributed model of resistance and capacitance. The term distributed means we can divide the long metal line into several segments, and we can calculate the parasitic resistance and capacitance for each segment. If we divide it into n segments, we can determine the total delay. Using this distributed model, the total delay can be calculated as half of the resistance multiplied by the length. In the previous lecture, we also demonstrated this, right? The metal line, along with the surrounding metal lines, whether it's its sidewalls or its surface, forms a parallel plate capacitor structure. So it exhibits parasitic capacitance. Additionally, since it's made of metal, it inherently has resistance, which leads to parasitic resistance. With parasitic capacitance and resistance, our wire is no longer an ideal conductor, as we might assume in our schematic design, where nodes have no parasitic resistance or capacitance. In reality, once the layout is processed, it carries these parasitic properties. So, if we use this metal line to transmit a signal, for example, a digital control signal or a clock signal, the signal that comes out at the end of the metal line may look like a red line, indicating that it has a certain delay compared to the input signal. This means that the parasitic resistance and capacitance can cause signal dispersion. What does this mean? It means that due to the presence of resistance and capacitance, the metal line responds to different frequency components of the signal at different speeds. Overall, the output signal will experience a delay. How much delay are we talking about? We typically calculate this delay using a distributed model of resistance and capacitance. The term distributed means we can divide the long metal line into several segments, and we can calculate the parasitic resistance and capacitance for each segment. If we divide it into n segments, we can determine the total delay. Using this distributed model, the total delay can be calculated as half of the total resistance multiplied by the total capacitance. So, if we have something like Ru and Cu, where Ru and Cu represent the unit length parasitic resistance and capacitance, we can find the total parasitic resistance of the entire line by multiplying Ru by L, where L is the length of the line. Similarly, the total capacitance of the line can be found by multiplying Cu by L. Therefore, using this distributed model, we can calculate the delay. Then Nr is multiplied together by Nl, which is to say, in this calculation, equivalent to 1, 12 of R. So we multiply this by C total. I wrote this wrong. It should be C, which is C total. This is a delay information calculated using the distributed model. Now going back to our wire, if we have something like Ru and Cu, What are Ru and Cu? They represent the unit length parasitic resistance and capacitance. Once we have that, let's see what the total parasitic resistance of the entire wire is. Isn't it just Ru multiplied by L, right? The unit length parasitic resistance is Ru and the length is L, so Ru multiplied by L gives us the total parasitic resistance of the wire. Next, let's look at the total capacitance of the wire, which is Cu multiplied by L. Cu is the unit length parasitic capacitance, and when we multiply it by the total length, we get the total parasitic capacitance. Therefore, using this distributed model, the calculated delay is 1/2 of Ru multiplied by Cu multiplied by L squared. So, as you can see, a real wire will experience signal delay due to the presence of parasitic resistance and capacitance. So, 1/2 of Ru multiplied by Cu multiplied by L squared is the result. As you can see, a real wire will experience signal delay due to the presence of parasitic resistance and capacitance. To estimate delay, calculate resistance and capacitance using square resistance. A metal line is a rectangular prism with length L, width W, and thickness T. Resistance is resistivity over thickness times length over width. R square, or square resistance, is resistivity over thickness, crucial for metal line resistance. In a specific process, resistivity and thickness are constant, making R square fixed. Process docs provide R square for each metal layer. Calculate resistance between A and B using R square times L over W. L over W shows square count in the strip. The concept of sheet resistance, also known as square resistance, is used to calculate the base resistance. Let's take a look at what square resistance is. Suppose we have processed a metal line in this base circuit technology. In reality, it forms a rectangular prism, right? This conductor is a rectangular prism. If we send a signal from point A and receive it at point B, this is the conductor. Its length is L, the width of the metal line is W, and it has a thickness, which we'll call T. So, for this rectangular conductor, how much resistance does it have? What is the resistance between A and B? The calculation of this resistance is quite simple. It should equal the formula. Resistance equals resistivity divided by thickness times length divided by width. Here, what is Rho? Rho is the resistivity of the material. Now, if we slightly rearrange this formula, we can express it as R equals R square times L divided by W. What is R square? R square equals Rho divided by T, right? So R square is resistivity divided by thickness. This R square is what we refer to as square resistance. The concept of square resistance is very important because it allows us to easily calculate the body resistance of such a metal line. Now, let's look at why we define square resistance and what its benefits are. First, let's see what R2 equals. R2 equals Rho divided by T. For a specific integrated circuit process, the material used for the metal interconnects is fixed. For example, if we use aluminum wiring, then Rho should be the resistivity of aluminum, and T is the thickness of the material. In integrated circuit processes, the thickness of the metal is fixed. Different layers may have some variations, but it is always a fixed value. For instance, in the example we mentioned earlier, in 180 nanometer technology, the metal thickness is about 0.5 micrometers. Regardless, it is a determined value. In other words, for a specific integrated circuit process, both the resistivity and the metal thickness are fixed. This means R2 is a constant value. R2 does not change. Therefore, generally speaking, in the documentation for integrated circuit processes, which includes the process parameters, it will provide the R2 value for each layer of metal, which is the square resistance for each layer of metal. Once we have the square resistance, we can calculate the integrated resistance between A and B directly using the formula R2 times L divided by W. This gives us the total base resistance. Now, let's look at what L times L divided by W means. If we draw a diagram, it looks like this. We have a metal line with a length of L and a width of W. So, L divided by W indicates how many squares fit into this long strip, right? So, L divided by W is essentially counting how many squares are in here. Let's count how many squares there are, and then we can calculate how large the base resistance is. Once we have the parameter of square resistance, calculating the base resistance of the wire becomes very easy. We just need to look at the number of squares and completely ignore the thickness issue. For example, let's say we draw a material that is 10 micrometers long and 2 micrometers wide, like this metal. Now, let's see how many squares are in here. There are definitely 5 squares, right? There are 5 squares that are 2 by 2, which means 2 micrometers by 2 micrometers. So that gives us 5 square units. Now, if the square resistance of this material is, say, 0.1 ohms per square, then we calculate that the total resistance is 0.5 ohms. So, through this method, we can quickly calculate the total resistance. Now, if instead of 2 micrometers we have 2.5 micrometers, we can use 10 divided by 2.5. How much is that? That's 4 squares. So we have 4 square resistances. If each square is 0.1 ohms, then that gives us a base resistance of 0.4 ohms. So, as you can see, once we have the squares, estimating the base resistance becomes just a matter of counting the number of squares. This is the concept of square resistance. Now, let's look at an example. Let's use metal 1 to draw a wire. Suppose its square resistance, R square, is 0.1 ohms per square. We draw a line 1 mm long and 200 mm wide. To find its base resistance, calculate the number of squares by dividing length by width. The length is 1000 micrometers and the width is 0.2 micrometers. Dividing 1000 by 0.2 gives 5000 squares. Each square is 0.1 ohms, so the total resistance is 500 ohms. Besides estimating delay, we can estimate the IR drop. This is crucial when using metal wire to transmit power. If a circuit module needs 1 mA and the wire has 500 ohms resistance, the voltage drops by I times R, or 500 MV. The voltage at the node becomes VDD minus 500 MV. The circuit must tolerate this drop. If only 300 MV is tolerable, the wire width must be adjusted. Wider wires have fewer squares, reducing resistance. For example, changing the width to 1 micrometer reduces squares to 1000. This affects the IR drop, which is vital in layout design to prevent circuit failure. So, with the base resistance, besides estimating the delay information, what else can we estimate? We can also estimate another very important piece of information, which is the IR drop issue. Why is this so important? Because when we use this metal wire to transmit power to a circuit module, for example, the metal wire connects to a circuit module to supply power, say VDD. The current will definitely flow from the power source to the module, right? Now, if we estimate the resistance using square resistance, we find that the total resistance is 500 ohms. The designer knows how much current the circuit module needs, right? For instance, if it requires 1 milliamp of current, and this current flows through a metal wire with a base resistance of 500 ohms, what happens? The voltage at this node will drop below VDD. By how much? It's I times R, right? We can calculate the IR drop by multiplying the current flowing through the metal wire by its base resistance. So, I is 1 milliamp, and R is 500 ohms, which gives us 500 millivolts. Therefore, at this node, the voltage has dropped to VDD minus 500 millivolts. After this drop of 500 millivolts, can the circuit still work? The circuit designer must specify the minimum voltage it can tolerate. For example, if the designer says this point can only tolerate a drop of 300 millivolts, then the layout designer knows how wide to draw the wire, right? Because the circuit designer has told you that the module can only tolerate a drop of 300 millivolts, and it has also specified the current. You need to calculate how wide the wire should be to meet the circuit's requirements. The wider the wire, the fewer squares it has. For instance, if the width is currently 200 nanometers, it has 5,000 squares. If we change it to 1 micrometer, then the number of squares drops to 1,000. Consequently, the base resistance decreases as well. This way, we can calculate the IR drop caused by this wire, which is very important. When designing the layout, you must consider the IR drop issue. Otherwise, after you draw it, the actual voltage received by the circuit module may drop so low that it can no longer meet its normal operating requirements, leading to circuit failure. This is very important. All right, so earlier we talked about how to calculate the parasitic resistance of metal wires, right? Now let's take a look at the phenomenon of parasitic capacitance. We actually mentioned parasitic capacitance in the last lecture, right? It's because metal wires have a certain thickness, so their sidewalls will have some parasitic effects with the sidewalls of adjacent metal wires. Also, the surface of the metal will have parasitic effects with other surfaces. For example, if we draw a technical line like this, since it has a thickness, we need to consider its three-dimensional structure. Now, how do we calculate this parasitic capacitance? The calculation of parasitic capacitance is a bit more complex compared to resistance calculations. There are two parasitic phenomena. The first one is called plate capacitance. Plate and parasitic capacitance form between metal surfaces akin to parallel plate capacitors. Estimate size using parasitic capacitance per unit area, A per square micrometer. A is 10 × 10⁻⁸, smaller than the illegal method's 10 × 10⁻⁵, due to small parasitic capacitance in circuits. It's significant with long wires. Planar capacitance forms between adjacent planes like poly to substrate. Estimate by multiplying parasitic capacitance per unit area by area. Edge capacitance, or fringe cap, comes from metal's side surface using alpha femtomicrometer units. So, as you can see, to estimate the size of the capacitance, we can actually use the parasitic capacitance per unit area for calculations. Its unit is A per square micrometer. Now pay attention, there's a new magnitude here called A, right? What we commonly see is, for example, the P method, which is 10 to the power of 12, right? And then there's the illegal method, which is 10 to the power of 15, right? Now we have another one that's even lower than the illegal method, called A, which is 10 to the power of 18, meaning it's 1,000th of the illegal method. Why is it so small? Because in integrated circuits, the parasitic capacitance, when viewed from its unit perspective, is relatively small. However, even though it's at the A level, this parasitic capacitance cannot be ignored. Once the metal wire is particularly long, this parasitic effect can also be quite significant. Now let's take a look at the planar capacitance. It's about which planes might form parasitic capacitance. From this table, we can see that the poly to the substrate, or our long oxide, can form such a planar parasitic capacitance. Also, metal to the substrate and metal to the doped region can form parasitic capacitance. This applies to metal too as well. So, whenever there are two adjacent planes, there's a possibility of generating planar capacitance. To estimate the parasitic capacitance of planar capacitance, we simply multiply the parasitic capacitance per unit area by its area, right? So, for example, if I have a metal wire with a length of L and a width of W, its surface area would be L times W, right? We can calculate the contribution of parasitic capacitance to the planar capacitance by multiplying this area by the parasitic capacitance per unit area. Now, there's another type of capacitance called edge capacitance or fringe cap. How does it come about? It's contributed by the side surface of the metal. When calculating it, you must pay attention that the metal has two side surfaces. When we calculate the parasitic capacitance of the side surface, the unit needs to change. It becomes alpha femtomicrometer. You might be curious why we use unit area for the upper surface but unit length for the side surface. This is because the side surface is definitely related to the parallel plate capacitor formed with some other side surface, right? The capacitance formed by the side surface is certainly related to the area of the side surface, so it should also be calculated per unit area. But why does it change to unit length? You need to pay attention here because when we calculate the side surface, the thickness of the side surface, in other words, the height of the side surface is fixed. This is determined by the processing thickness of, for example, M1, right? The thickness of M1 is determined by the process and is fixed, meaning it won't change. So when you calculate this parasitic capacitance, you don't need to worry about the thickness. Therefore, when you calculate it, it becomes a matter of measuring its length, right? You just need to count how long it is, so it's given as a unit length. Curious why we use unit area for the upper surface but unit length for the side surface, because the side surface relates to the parallel plate capacitor formed with another side surface. The capacitance calculated from the side surface relates to the area of the side surface, so it should be calculated per unit area, but why change to unit length? Simply, when we calculate the side surface, its thickness. The height of the side surface is fixed. Like M1, the thickness is determined by the manufacturing process and is fixed, so it's fixed. Thus, when you calculate this parasitic capacitance, you don't need to worry about the thickness. Thus, when you calculate it, it becomes measuring its length. You just need to count how long it is, hence it's given as a unit length. This is why we refer to it as line capacitance. In other words, the height of the side surface is fixed. This is because, for example, this is M1, right? The thickness of M1 is determined by the manufacturing process, and it is fixed and will not change. So when you calculate this parasitic capacitance, you don't need to worry about the thickness. Therefore, when you calculate it, it becomes a matter of measuring its length, right? You just need to count how long it is, so it's given as a unit length. This is why we refer to it as line capacitance. So we usually refer to this as line capacitance. Calculating length helps determine capacitance size. Parasitic capacitance varies with materials, affecting line capacitance. This method estimates wire capacitance. Parasitic capacitance is everywhere in circuits, causing crosstalk and affecting signal purity, leading to performance decline. We'll discuss shielding against these interferences. In an integrated circuit with a P substrate, M1 and M2 layers show parasitic capacitance, M1s. Let's take a look at this diagram illustrating the existence of parasitic capacitance. In this circuit, parasitic capacitance is actually everywhere. Through these parasitic capacitances, signals can form a lot of crosstalk, which can affect the purity of our signals. This in turn can lead to a decline in the performance of our circuit blocks. That's why we will later specifically discuss how to shield against these interferences, which are essentially noise. For example, here is an integrated circuit with a P substrate, and this is M1, and let's say this is M2. We can see that there are different sections of M1 and 4 sections of M2. Now, looking at the surfaces of M1, both the top and bottom surfaces will have parasitic capacitance with other surfaces. For instance, there is parasitic capacitance between the bottom surface of M1 and the substrate. The top surface of M1 and the bottom surface of M2 will also have parasitic capacitance, which we just referred to as plate capacitance. Additionally, the sides of M1 will also have parasitic capacitance with other sides. For example, the side of M1 will have parasitic capacitance with the side of the adjacent M1, and it will also have parasitic capacitance with the surface of the substrate. The side of the capacitor will also have parasitic capacitance with the side of MR. This is what we referred to earlier as fringe capacitance. So as you can see, parasitic capacitance is everywhere. Now let's look at the three-dimensional structure, which gives a clearer picture. For instance, we have a substrate, and on top of it, we have 5 M1s. On top of M1, there are 2 M2s, and on top of M2, there are 5 M3s. You can see that there is parasitic capacitance everywhere between these structures. For example, there is parasitic capacitance between the two sides of M1, and the side of M1 and the side of M2 may also have parasitic capacitance. The top surface of M1 and the bottom surface of M2 have parasitic capacitance, and the bottom surface of M1 and the substrate also have parasitic capacitance. The same goes for M2 and M3. So after drawing multiple layers, we can see that this parasitic phenomenon exists everywhere. Using square resistance and plate cap and fridge cap discussed, estimate wire body resistance and capacitance, right? Using square resistance, calculate body resistance, simultaneously estimate airdrop issue from body resistance. This prevents wires' insufficient width causing voltage drop, leading to power issues. We use plate cap and fridge cap to calculate parasitic resistance. Combining parasitic with total resistance, we use distributed resistor-capacitor model discussed to calculate RC delay, right? This shows signal delay. For example, we have M1 to find plate capacitance and fringe capacitance, planar capacitance 23 AF per square micron, and fringe capacitance 79 AF per micron. Line thickness 1 micron. If a metal line is 1 mm long and 200 nm wide, we calculate signal delay through it. Using the distributed model delay formula, 1/2 of R total multiplied by C total, right? Calculate R total and C total for delay. First, R total. R total is calculated as before. A 1 mm long, 200 nanometer wide line. Convert 1 mm to 1000 microns, divide by 0.2 microns, giving 5000 squares. Body resistance 500 ohms. Now capacitance. Now, let's look at the values for plate capacitance and fringe capacitance. The planar capacitance is 23 AF per square micron, and the line capacitance or fringe capacitance is 79 AF per micron. Also, the thickness of the line is given as 1 micron. So if we take a metal line that is 1 millimeter long and 200 nanometers wide, we can calculate how much delay the signal will experience as it passes through this metal line, right? For the delay, we can use the distributed model, and the formula is 1/2 of R total multiplied by C total. So we just need to calculate the values of R total and C total to find the delay. Let's first look at R total. R total is calculated the same way as before. It's a 1 millimeter long and 200 nanometer wide line. We convert 1 millimeter to 1000 microns and divide by 0.2 microns, which gives us 5000 squares, right? So the body resistance is the same as before, which is 500 ohms. Now let's check its capacitance. Let's take a look at this capacitance. First, we need to calculate the plate capacitance, right? For the planar capacitance, let's check its area. How big is the area? It's 1000 micrometers long and 0.2 micrometers wide, right? So 1000 multiplied by 0.2 gives us 200 square micrometers. That's the area of the planar capacitance. Now what's the unit area? It's 23A, right? So we multiply 200 square micrometers by 23A per square micrometer, and that gives us the plate capacitance. Now let's look at the line capacitance. The line capacitance can be calculated by simply multiplying by the length, right? The unit length is 79A. So how long is the length? It's 1000 micrometers. We need to remember that it only has two sides, so we multiply by 2. Adding everything together gives us a total of 162. 162 is illegal. Multiply by resistance, divide by 2 for 40.5 ps delay. This affects analog and digital signals, limiting distortion. Layout must consider line size to meet constraints. Delay estimate is rough due to complex capacitance and parasitics. Accurate delay needs PECs for real parasitic extraction and verification. Metal is primary, vias connect layers. Contacts link substrate to metal. For M1 to M4, stack vias and metals. Top view shows M1 to M4 connection by stacking. Vias are crucial. Whether it's for transmitting an analog signal or a digital signal, designers definitely have constraints on how much distortion the signal can tolerate, right? So when you're laying out the circuit, you'll judge whether the length or width of the line can meet those requirements based on these constraints using a simple estimation. Of course, this estimation is quite rough because, as we just saw, both planar capacitance and line capacitance are very complex. The parasitics between different surfaces are not the same, so this is just a general estimate when drawing. Ultimately, to find out how much delay it actually causes, we need to use PECs, which is post-extraction, to extract the real parasitic situation and then use that more accurate distributed model to feed back into our schematic and perform post-layout verification. This way, we can finally determine how much delay this line actually has. The post-layout verification provides a more precise evaluation. Now, the above is about the most commonly used layer, which is metal. The second most commonly used layer is actually vias. Vias connect different layers of metal, right? These different layers of metal are at different heights, and there is an insulating medium between them so they don't electrically connect with each other. If we want to connect them, we must use vias. Let's take a look at a schematic of this three-dimensional structure. Suppose the bottom is the substrate, and this is metal 1, which is the first layer of metal. What do we use to connect the substrate to the first layer of metal? We don't use vias here, we use contacts. Contacts are used to connect the substrate to the metal, or to dope the metal, or to connect the gate to the lower metal layer. All of this is called contacts. Then, to connect metal 1 to metal 2, we use a via. For metal 2 to metal 3, we use via 2, and for metal 3 to metal 4, we use via 3. If you have M5, there will be via 4 as well. So you can see that if I want to connect M1 directly to M4, I must draw this three-dimensional structure to complete the connection. Now let's look at the top view, which is actually the result of our layout drawing. We draw a blue line for M1, and then we draw M4 in the vertical direction. If we want to connect M1 and M4, what do we need to do at this position? We need to stack several layers. First, we need to draw via 1, then we need to draw M2 because via 1 must connect to M2 first. So we draw M2, then we draw via 2, and then we draw M3. And finally, we draw via 3 to connect to M4. So when you're drawing, you actually need to overlap several layers at this position, stacking all the metals and vias together to connect M1 to M4. That's the role of vias. Then you need to draw another V3 to connect to M4. So when you're drawing at this position, you actually need to overlap several layers. You have to stack all the metals together and overlap all the vias so that you can connect M1 to M4. That's the role of vias.
Let's take a look at the next topic, which is called the active region. The role of the active region is actually to define the positions of our devices or contact points. We need to use the active region for this definition. In the first lecture, when we talked about the process flow, you could see the role of the active region, right? In the entire circuit, aside from the gas pad, all other positions are actually what we call fueled oxide, which is oxide formation. In advanced processes, we use STI, which stands for shallow trench isolation. Only the active region does not have this isolation. Here we can process the gas pad, so the areas where we open long bites or remove the RSTI isolation are the active regions. This is the role of the active region. Our friction key must be formed within the active region. Now, moving on to polysilicon. The first very important role of polysilicon is that it is used to form the gate of our MOSFET to create the ridge. Essentially, as long as we draw an active region on the layout and then overlap a gate on top of that active region, we have already formed the basic structure of the MOSFET. The gate is made of polysilicon. Of course, this polysilicon needs to connect to M1 as we just discussed, and it connects through a contact. This is the role of polysilicon. Polysilicon actually has a second role as well. It can also serve as a signal interconnect line, similar to M1. Just like M1 can be used for signal interconnection, polysilicon can also act as a wire. However, the problem is that its parasitic resistance is relatively high. The parasitic resistance of polysilicon can reach 200 ohms per square, while the parasitic resistance of metal is generally around 0.1 ohms per square. So you can see there's nearly a 2,000-fold difference between them. Polysilicon's primary role is forming the MOSFET gate. By drawing an active region and overlapping a gate, the basic MOSFET structure is formed. This gate, made of polysilicon, connects to M1 through a contact. Polysilicon also serves as a signal interconnect line like M1, but with high parasitic resistance, 200 ohms per square compared to metal's 0.1 ohms. This 2,000-fold difference means polysilicon is rarely used for interconnects unless necessary. It can save space for short, slow signal paths, but its high resistance limits long-distance use. So the gate is made of polysilicon, right? Of course, this polysilicon needs to connect to M1 as we just discussed, and it connects through a contact. That's the role of polysilicon. Actually, polysilicon has a second role as well. What is it? It can also serve as a signal interconnect line, similar to M1. Just like M1 can be used for signal interconnection, polysilicon can also act as a wire. However, the problem is that its parasitic resistance is relatively high. The parasitic resistance of polysilicon can reach 200 ohms per square, while the parasitic resistance of metal is generally around 0.1 ohms per square. So you can see there's nearly a 2,000-fold difference between them. Therefore, polysilicon is generally not used as an interconnect line unless absolutely necessary. However, sometimes to save space, and if the signal interconnect distance is very short, or the signal transmission is very slow, you can use polysilicon for interconnection. But you must pay attention to its parasitic resistance issue. You can't use polysilicon for long-distance interconnects. So, it is only suitable for short-distance interconnections. This is something to be very careful about. It is only suitable for short distances. Later, we will discuss the situations in which we might use polysilicon for interconnect lines. Generally, polysilicon won't be used for interconnect lines unless absolutely necessary. However, sometimes to save space, and if the signal interconnect distance is very short, or the signal transmission is very slow, you can use polysilicon for interconnection. But you must pay attention to its parasitic resistance issue. You can't use polysilicon for long-distance interconnects. So, it is only suitable, right? You see, it says here that it is only suitable for short-distance interconnections. Just short-distance interconnect lines. This is something to be very careful about. It is only suitable for short distances. Later, we will discuss the situations in which we might use polysilicon for interconnect lines. So the layers we talked about are the most commonly used ones that has the metal contact regions, vias, and poly layers. Besides these, what else is there? Let's take a look at this list with some layers commonly used in this process. There are some abbreviations here, so let's go through them one by one. First, we have active. We mentioned the contact region and the N-well. The N-well injection is used to define the N-well. In our previous discussion, we looked at the process flow and layout for fabricating a PMOS where we mentioned the N-well. What else do we have? There's TGOT. What is TGOT? It stands for triple gate oxide. Why do we have this? It's used to define the back oxide layer. In the current CMOS process, it provides 2 voltage supply modes. In the 180 nanometer process, it might provide a 3.3 V supply and a 1.8 V supply. Why do we do this? As the 1.8 V devices can be made with smaller dimensions, which enables the creation of digital circuits. Digital circuits use lower voltages, while analog circuits tend to be different. Analog circuits don't pursue very small channel lengths, as if the channel length is too small. The overall characteristics of the circuit can suffer due to the short channel effects, and their impedance won't be very high. Analog circuits favor longer channel lengths, which results in thicker channels. A higher supply voltage brings another benefit. It enables larger signal swings, which enhances the signal-to-noise ratio. So analog circuits often favor higher voltages, which means 3.3 V might be used for analog circuits. This means on the same process platform, I need to fabricate both 3.3 V mode devices and 1.8 V mode devices. The thick of the gate oxide under these two types of devices is different. The gate oxide for 1.8 V needs to be thinner, while for 3.3 V, since it has to withstand a higher voltage, the gate oxide must be thicker. So we need a layer to differentiate between these, which is the TGOT. When we discuss the devices, we will see what the exact role of TGOT is. There's the gate or poly used to form the ridge and can be used for short-distance interconnections. We have the injections, which include P-type injection, P+, and N-type injection, N+. The 1.8 V devices can be made with smaller dimensions, enabling digital circuits. Digital circuits use lower voltages, but analog circuits? Analog circuits don't use very small channels, as very small channels can degrade circuit performance due to short channel effects and low impedance. Thus, analog circuits prefer longer, thicker channels. Higher voltages allow larger signal swings, improving signal-to-noise ratio. Thus, analog circuits often use higher voltages like 3.3 V. This means fabricating both 3.3 V and 1.8 V devices on the same platform. The gate oxide thickness differs for these devices. 1.8 V gate oxide is thinner, while 3.3 V needs thicker oxide for higher voltage. We need TGOT to distinguish these. We will later discuss TGOT's role. Gate, or poly, forms the ridge and is used for short interconnections. Then, P-type, P+, and N-type, N+ injections. These layers form device modes. Remaining layers are for contacts and metal vias for interconnections. These layers are commonly used in layouts. Besides these, processes provide auxiliary layers. The 3.3 V supply might be used for the analog circuit. It means that on the same process platform, I need to make 3.3 V and 1.8 V devices. Their gate oxide thickness differs. 1.8 V devices need thinner gate oxide. 3.3 V devices need thicker. We need TGOT to distinguish them. We will discuss TGOT's role later. Gate, or poly, forms the ridge and is used for short interconnections. Then P+ and N+ injections. These layers form device modes. Remaining layers are for contacts and metal vias for interconnections. These layers are common in layouts. Besides, there are many auxiliary layers. Some layers have real photomasks. Asterisk-marked layers have photomasks. M1 layer has a real M1 photomask. Some are auxiliary, like RPDMI. It defines a resistor. It helps software like Calibers, LREs, and DRC recognize resistors. Some auxiliary layers serve these purposes. These layers form device modes, with others for contacts and metal vias, all for interconnection. They're common in layout drawings. Besides these, a process provides auxiliary layers. Some layers have real photomasks, like those marked with asterisks. For example, the M1 layer has a corresponding photomask. Auxiliary layers like RPDMI define resistor devices, helping software like Calibers, LREs, and DRC recognize resistors. These layers inform software during layout design but aren't used in fabrication. This distinguishes commonly used layers. It's important to note that some of these layers have real photomasks
corresponding to them. For example, the layers marked with asterisks here all have real photomasks associated with them. For instance, the M1 layer definitely has a corresponding M1 photomask, and that exists in reality. Then there are some layers that are auxiliary layers, like the RP-DAMI layer. This is an auxiliary layer, and you can tell from its description that it's used to define a resistor device. So, its main purpose is to help the software, particularly tools like calibers, LREs, and DRC, to recognize that this is a resistor and not something else. Therefore, there are some auxiliary layers that serve these purposes. These layers don't have real photomasks corresponding to them. They are just there to inform the software during layout design that this is a resistor. It doesn't mean that we will use these layers during fabrication. So, that's the distinction for these layers that we commonly use. In this layer of the layout, the next part is about failure stimuli in circuits. This part is also very important because when we are drawing the layout, we must pay attention to these failure stimuli. Otherwise, it could lead to a poorly designed layout that doesn't consider these issues, ultimately resulting in a circuit that fails during manufacturing. Let's explore failure stimuli mechanisms. The first is the antenna effect. What is this effect? Consider an example. When designing a layout, we draw a MOSFET. The MOSFET's gate is red, representing its ridge, while green shows source and drain regions. The gate connects through a metal line for signal interconnection via a contact shown in black, then to M1, a light blue metal line. If this line is long or large during metal processing, a material called etching gas is used. Plasma absorbed by the metal means it absorbs charged particles, leading to voltage on the line. If this voltage exceeds a threshold, the red part is the gate, it's the ridge of the gate. The green part is the source and drain regions. This is the source and this is the drain. This is one of the devices. The gate always needs to be connected through a metal line to create a signal interconnection. I connect it through a contact shown in black. I connect it to M1. The blue part, this light blue strip, is M1, a metal line. If this metal line is very long or has a large area, it can lead to an issue when, during metal processing in integrated circuits, a material called an etching gas is used. During this etching step, some plasma can be absorbed by the metal. The metal will absorb a lot of charged ions. After absorbing many charged particles, there will be a voltage on the metal line. When this voltage is high, if it surpasses a threshold, it can be an issue. If our gate oxide is 40 nanometers deep and the maximum electric field intensity it can withstand is 4 times 10 to the power of 6 volts per centimeter, if the electric field intensity surpasses this value, the gate oxide might break down. If the gate oxide is 40 nanometers deep, it can withstand a voltage of 16 volts. The higher the voltage, the higher the electric field intensity, and if it surpasses 4 times 10 to the power of 6 volts per centimeter, the gate oxide will break down. During etching, the metal absorbs a large number of charged ions, causing the voltage to rise. If your metal line is very long or has a large area, it might surpass this threshold of 16 volts. It might harm the gate oxide. Once that happens, the device fails. The gate oxide has broken down and the device is no longer working. This failure occurs during manufacturing due to the antenna effect. When connecting the gate, if the interconnect line is very long, be cautious. You should prevent this problem during the early design stage. DRC checks can help catch these issues. Some foundries have a check file for the antenna effect to identify where it might occur. Make changes as needed. The best practice is to keep this in mind while drawing the layout. If you connect things without considering these factors, relying only on checks, some issues might be hard to resolve. During the early design stage, you need to be aware of these aspects. If the voltage exceeds the electric field strength gate withstands, if our gate oxide is 40 nanometers thick and the max field strength it handles is 4 times 10 to the power of 6 volts per centimeter, then if the electric field strength exceeds this value, the gate oxide could break down. If the gate oxide is 40 nanometers thick, it can withstand a voltage of 16 volts. The higher the voltage, the higher the electric field strength, and if it exceeds 4 times 10 to the power of 6 volts per centimeter, the gate oxide will break down. During the etching process, the metal absorbs many charged particles, which causes the voltage to rise. If your metal line is long or large, it could exceed this threshold of 16 volts. This can damage the gate oxide. Gate oxide damage means device failure. This failure occurs during manufacturing due to the antenna effect. When connecting the gate, be cautious of long interconnect lines. Avoid this in the design phase. DRC checks can catch these issues. Some foundries have specific checks for the antenna effect. Make modifications accordingly. Best practice. Keep this in mind during layout. Connecting without considering these factors can make issues hard to resolve. Pay attention to this during initial layout. If a long gate interconnect is needed, use jumpers. If your metal line is particularly long or has a large area, it could exceed the threshold of 16 volts. If that happens, it can damage the gate oxide, and once it's damaged, the device has already failed.
the gate oxide has broken down and the device is no longer functional. This type of failure doesn't occur after the chip is powered on. It happens during the chip manufacturing process due to the antenna effect. So, when you're connecting the gate, if you notice that the interconnect line is particularly long, you need to be very careful. You should avoid this issue during the initial design phase. Of course, DRC checks can help catch these issues. Some foundries may have a separate check file specifically for the antenna effect, which can identify where the antenna effect might occur. You can then make modifications accordingly. However, the best practice is to keep this in mind while you're drawing the layout. If you just connect things without considering these factors, relying solely on checks to catch errors, some issues might be difficult to resolve. So, during the initial layout phase, you need to pay enough attention to this issue and consider it seriously. If you really need the gate interconnect line to be long, how can you solve this problem? There are two common methods to address this issue. The most commonly used method is to use jumpers. We call this using a jumper to solve the problem. It's important to note that these jumpers should be high-level jumpers. We need to pay enough attention to this issue and consider it carefully. This is a matter of great importance and requires our full focus and careful consideration. If we really need the gate interconnect line to be long, how can we solve this problem? This is a question that requires deep thought and analysis. There are two common methods to address this issue. The most commonly used method is to use jumpers. We call this using a jumper to solve the problem. This method is widely recognized and implemented in various scenarios, so everyone needs to pay attention that these jumpers must be high-level jumpers. To jump to a higher level means that this jumper must connect to a higher metal layer. Jumping to a lower layer is useless. Why is that? Let's take a look. For example, this deep blue metal line is M1, right? And this light green one is, let's say, M2. Now we have a problem with M1, which is particularly long. During the processing of M1, it absorbed a lot of charged particles, causing the gap to break down. To avoid this kind of failure, we need to cut M1 near the gate, make sure it's close to the gate. We cut M1 right here, and cutting it means that the left part of M1 and the right part of M1 are no longer connected, right? They are disconnected. So, what do we do about the signal that isn't connected? We still need to connect the signal. How do we do that? We connect it through M2. By doing this, the signal is connected again. If we were to draw a diagram, it would look something like this. M1 is originally very long, but we cut it at this point. So there's no connection here, right? No connection. And this position is where our MOSFET is located. It's the peak of the MOSFET. So how do we connect the signal group? We connect it to the via V1 and link it to M2. This is M2 and this is M1. We connect via V1 to M2 to solve the issue. Now, why does this work? This brings us to the processing engineering aspect. Once we finish processing M1, after a certain time, we need to use some methods to draw out all the charges from the metal on the entire chip. Once all the charges are drained, the voltage on that metal decreases, right? Then we can process the next layer of metal, which will absorb the charges caused by the next layer of metal. So, when we process M1, how do we connect the signal group? Connect via V1 to M2, right? This is M2 and M1. Connect V1 to M2 to solve it. Why does this work? It relates to processing engineering. After processing M1, we must draw out all charges from the metal on the chip. Once charges are drained, the voltage decreases, right? Then we process the next metal layer, which absorbs charges from it. When processing M1, it's long. Even cut, the left side is long, absorbing much charge. But the voltage increase won't connect to the gate, right? It's disconnected. This metal isn't connected to our peak, so its voltage rise doesn't affect the gate. We must extract charges from the chip metal. Once drained, the metal voltage drops. Then process the next metal layer, absorbing its charges. Processing M1, it is long. Even cut, M1's left is long, absorbing much charge. But this charge's voltage rise won't connect to the gate, as it's disconnected. This metal isn't connected to our peak, so its voltage rise doesn't affect the gate. The metal directly connecting to the gate is short, and its charge-induced voltage rise isn't enough for gate breakdown, so no problem. Thus, cut close to the gate. Cutting further makes no sense, as the line to the gate remains long, with high charge. M1 is long. After cutting, it remains long, absorbing charge. This charge doesn't reach the gate due to disconnection. The metal isn't linked to our peak, so its voltage rise doesn't affect the gate. The metal connected to the gate is short, and its charge-induced voltage isn't enough to cause a breakdown, so no issue. We need to cut close to the gate. Cutting further away keeps the line long, maintaining high charge, which isn't protective. Charge on the left can't reach the gate. Once M1 is processed, this charge is released, dropping M1's voltage to 0, resolving the issue. M1 is fine, allowing us to process M2. M2 absorbs little charge due to its short jumper, preventing gate breakdown. M2's small area means its charge doesn't significantly impact the gate. This method method effectively addresses antenna issues. The need to jump to a higher metal layer relates to the processing sequence. The short metal connected to the gate prevents voltage breakdowns. Cuts should be near the gate to avoid long lines that keep high charge. After cutting, charge on the left can't reach the gate. Processing M1 releases this charge, ensuring safety. M1 is then fine, allowing M2 processing. M2's short jumper absorbs minimal charge, preventing gate breakdown. M2's small area minimizes impact on the gate. Jumping to a higher metal layer is necessary due to processing order. If M2 has issues, jumping to M1 doesn't help, as M2 remains connected to the gate. A higher layer jump is needed, as lower layer processing releases charge first. A small higher layer area won't affect the gate, even if the lower layer... So, this doesn't serve its protective purpose. We must cut it off close to the gate. After cutting, there will be a lot of charge on the left side, but it won't connect to the gate, right? Once we finish processing M1, this portion of charge will be released through some means. After it's released, the voltage on M1 will drop back down to 0, and everything will be fine. M1 will be okay, and then we can process M2. When we process M2, it will also absorb charge, right? But note that the jumper for M2 is very short, so it absorbs very little charge. The charge absorbed by M2 won't cause a breakdown at the gate either. So, while M2 is connected to M1, and the charge can be transmitted to the gate, because its area is so small, it won't have a significant impact on the gate. Through this method, we can effectively solve the issue of antenna up. From this process, you can see why we need to jump to a higher metal layer. It's related to the processing sequence. For example, if the blue one is M2 and it has a problem, would jumping to M1 help? No, it wouldn't. Because when you jump down to M1, during the processing of M2, M2 is still connected to the gate through M1. In the end, the voltage caused by the charge will still be applied to the gate, which won't work. It must be a jump to a higher metal layer because when processing lower metal layers, the charge is released after processing, and then we process the higher metal layer. As long as the area of the higher metal layer is small enough, it won't affect the gate. Even if the area or length of the lower metal layer is very large, it won't have a significant impact because you've already cut it off. This is why the jumper must be a high-level jumper to solve the antenna up issue. For instance, if we have a problem with M1, we jump to M2. If M2 has a problem, we jump to M3. If M3 has a problem, we jump to M4. Someone might ask, what if M4 also has a problem? What if M4 is very long and there's an antenna up issue? How do we solve that? Because we don't have M5 and M4 is the top metal layer, what do? We need to use another method, which is the second solution, adding a PN junction. If the blue one is M2 and there's a problem with it, would jumping to M1 help? No, it wouldn't, right? Because when you jump down to M1, during the processing of M2, M2 is still connected to the gate through M1. In the end, the voltage caused by the charge will still be applied to the gate, so that won't work. It must be a jump to a higher metal layer because when processing lower metal layers, after they are processed, the charges are released, and then we process the higher metal layer. As long as the area of the higher metal layer is small enough, it won't affect the gate. Even if the area or length of the lower metal layer is very large, it won't have a significant impact because you've already cut it off. This is why the jumper must be a high-level jumper to solve the issue of antenna up. For example, if we have a problem with M1, we jump to M2. If M2 has a problem, we jump to M3. If M3 has a problem, we jump to M4. Someone might ask, what if M4 also has a problem? What if M4 is very long and there's an antenna up issue? How do we solve that? Since we don't have M5 and M4 is the top metal layer, what do? We need to use another method, which is the second solution, adding a PN junction. If you don't want to use a jumper with M1, use a PN junction method. Use a reverse bias diode. Cathode connects to M1. A MOSFET source or drain replaces this junction. With an NMOS, connect the drain to metal, grounding substrate and source. The drain is N-type, substrate P-type, creating a parasitic junction. M1, being long, collects charge, raising voltage. A connected PN junction's reverse bias increases, leading to breakdown. The anode of this diode is grounded and the cathode is connected to M1. In practice, we often use the source or drain of a MOSFET to replace this kind of junction. For example, I have this NMOS, right? So we connect the drain to the metal, and both the substrate and the source are grounded. The drain is N-type and its substrate is P-type. Therefore, there is a parasitic junction between the drain and the substrate. We can use this to act as a junction connected to the circuit. Now, why does creating a junction provide protection? This utilizes the breakdown characteristics of the junction. We will also use this characteristic when we talk about ESD later. Let's take a look at M1, which is particularly long, right? During processing, it collects a large amount of charge, causing its voltage to rise sharply. When this voltage rises sharply, we find that we have a PN junction connected here, and the reverse bias voltage across this PN junction becomes very large. When the reverse bias is very high, what happens? Breakdown occurs, right? I believe everyone knows the IV characteristics of a PN junction. This is its voltage, V, and current, I. When we apply a reverse bias voltage, if the reverse bias is not very high, the current is very weak. However, once the reverse bias reaches a certain level, the current will surge. This is the breakdown point, right? When it reaches the breakdown voltage, V break, the current surges, flowing from the cathode to the anode. So the large amount of positive charge accumulated on the line will be released by this PN junction, sending it to the ground. This way, the voltage on M1 decreases, right? It decreases, so this protects the sensitive part. Essentially, it acts as a protective device, allowing it to guide away the large amount of charge, thus protecting the get. This is its voltage, V, and this is its current, I. When we apply a reverse bias voltage to it, if the reverse bias voltage is not very high, the current is very weak. However, once the reverse bias voltage reaches a certain level, the current will surge. This is the breakdown point, right? When it reaches the breakdown voltage, V break, the current surges, flowing from the cathode to the anode. So, the large amount of positive charge accumulated on the line will be released by this PN junction, sending it to the ground. This way, the voltage on M1 decreases, right? It decreases, so this protects the sensitive part. Essentially, it acts as a protective device, allowing it to guide away the large amount of charge, thus protecting the get. The large amount of positive charge accumulated on the line will be released by this PN junction, sending it to the ground. This way, the voltage on M1 decreases, right? It decreases, so this protects the sensitive part. Essentially, it's like adding a protective device that can guide away this large amount of charge, thus protecting the get. Diode area considerations are crucial. Large metal areas require increased diode area, addressing the antenna effect. The second issue is soft connection, common in layout. A MOSFET is a 4-terminal device: source, gate, drain, and substrate. The substrate connection is vital. If ignored, it floats and causes issues. The substrate is often overlooked. Forgetting the substrate leads to a soft connection. If the substrate contact is missing, the P substrate is affected. Soft connection is a failure in coarse layouts. A MOSFET has 4 terminals: source, gate, drain, and substrate. The substrate must be connected. If not, it floats, causing soft connections. The P substrate acts as the substrate, with contacts grounded elsewhere. Ideally, it should be at 0 potential, but parasitic resistance causes an IR drop, so the potential isn't 0 everywhere. Only at the contact is it 0. Elsewhere, it varies. A MOSFET in an inverter injects transient current into the substrate, flowing to the lowest potential, 0. Parasitic resistance causes voltage fluctuations. We've emphasized that a MOSFET is a 4-terminal device: source, gate, drain, and substrate. In design schematics, the substrate connection is crucial. If left unconnected, it will float and prompt you. However, in layout drawings, the substrate is often overlooked. For instance, after completing the source, gate, and drain of an NMOS, you might forget the substrate contact, leading to a soft connection. If the substrate contact is missing, the entire P substrate acts as the substrate, which might have contacts elsewhere, grounding it. Ideally, the P substrate should be at 0 potential, but due to parasitic resistance, it isn't. The resistance causes an IR drop, so the potential isn't 0 everywhere, only where the substrate contact is connected. Elsewhere, the potential varies. For example, a MOSFET in an inverter injects transient current into the substrate, flowing to the lowest potential, 0. However, due to parasitic resistance, the voltage isn't 0 and may fluctuate. This fluctuating current causes the substrate potential to rise or fluctuate, interfering with device operation. This is called a soft connection, meaning the connection isn't reliable. Therefore, ensure the device is solidly made. Now, regarding the P substrate, I might have substrate contacts at other locations. For example, I might have drawn a substrate contact at this position, grounding it. In an ideal situation, it seems like I've biased the entire P substrate to 0, so wouldn't the substrate of all NMOS devices at other locations also be at 0 potential? Actually, that's not the case. Why? Because the substrate's resistance is not 0, right? Its resistance cannot equal 0. It has a certain parasitic resistance. Once there is parasitic resistance, due to the IR drop issue, the potential won't be 0 everywhere. It won't be 0 everywhere. Only at the specific location where you have connected the substrate contact will the potential be 0. At other locations, the potential may vary. For instance, due to the operation of this MOSFET, like in an inverter that frequently toggles, it will inject a transient current into the substrate. Where does this current flow? It will definitely flow to the substrate, to the lowest potential, which is 0, right? It will follow the substrate to find the lowest potential, which is 0, to flow out. Because there is parasitic resistance on the substrate, the voltage at that position won't equal 0, it may even fluctuate. This is because the current is not a constant current, it is a fluctuating current. Since the current is fluctuating, when it flows through this resistance, it will generate a fluctuating voltage. So this can cause the substrate potential to either rise or fluctuate back and forth, which can interfere with the operation of the device. This phenomenon is what we call a soft connection. As the name suggests, it is connected, but the connection is not very reliable. It's soft. Therefore, we must ensure that this device is made solidly connected. What does it mean to be solidly connected? It means that once you draw a MOSFET, There must be a reliable substrate contact nearby. There must be a reliable substrate contact. Of course, this issue of soft connections can be checked with DRC. DRC can help with this. DRC will generally tell you that within a certain number of micrometers of a device, there must be a pickup, which is the term they use. So this can cause the substrate potential to either rise or fluctuate back and forth, which can interfere with the operation of the device. This phenomenon is what we call a soft connection. As the name suggests, it is connected, but the connection is not very reliable. It's soft. Therefore, we must ensure that this device is made solidly connected. What does it mean to be solidly connected? It means that once you draw a MOSFET, there must be a reliable substrate contact nearby. There must be a reliable substrate contact. Of course, this issue of soft connections can be checked with DRC. DRC can help with this. DRC will generally tell you that within a certain number of micrometers of a device, there must be a pickup, which is the term they use. To connect well means to make a solid connection, right? So what does a solid connection mean? It means that once you draw a MOSFET, there must be a reliable substrate contact nearby. There must be a reliable substrate contact. Of course, the issue of soft connections can be checked with DRC. DRC can help with this. DRC will generally tell you that within a certain number of micrometers of a device, there must be a pickup, which is the term they use. So when we talk about pickup, it's a bit like saying this is a collection point, right? A collection point means that around this device, you must have a pickup. There are certain distance requirements. For example, if it indicates that there's no pickup within 30 micrometers, then you know that there's no reliable connection within 30 micrometers of this device. So the substrate connection isn't very reliable, and you must ensure this is in place. This is for the P substrate. And of course, the N well has this issue too, right? The N well also has this problem. And for the N well, you need to have a contact for N plus as well. So there must be an N plus injection near the PMOS. If the well is particularly large and there's an N plus at one edge of the well but a PMOS at the other edge without any other N plus injection in between, then the substrate of this PMOS becomes unreliable, right? So the soft connection can occur with the P substrate, and the N well can also have soft connection issues. This is the phenomenon of soft connections. All right, the third failure mechanism is called latch-up, also known as the snapback effect. So what is this effect? Let's take a look at this structure. This effect usually occurs when we have a large NMOS and PMOS, particularly in the case of a very large inverter. The most typical situation is when we draw a very large inverter, which can lead to this problem. Why do we use particularly large inverters? They are used as buffers to buffer a digital signal. Why do we need to buffer? It's because if you have a particularly large load, you need a buffer that has a large size and strong output current capability. So, the width to length ratio will be very large. If the design of this inverter isn't reliable enough, it can lead to latch-up. Once the latch-up phenomenon occurs, the consequences are very serious. It can cause the device or even the chip to burn out directly. Now, let's see how it happens. First, we have an NMOS drawn on the P substrate, right? On the left is the NMOS, and on the right there's an N well, where we also have a PMOS. Now let's take a look at how these two devices form a parasitic structure. What does the circuit diagram of this parasitic structure look like? It resembles the shape on the right. Let's analyze a few components in this structure. First, we look at R1. R1 is the connection from the power supply to the external point. RE is the base resistance of the N well, linking N plus injection to the PMOS core. PMOS forms a PNP transistor, QE, with its collector as the external point and emitter to power. P substrate connects via resistance R to the D line. NMOS forms an NPN transistor, Q2, with its collector at the N well. Close NMOS and PMOS create a parasitic structure. Without current, point X is 0 volts, external point is VDD, keeping transistors off. Circuit operation injects current into the substrate, raising voltage at point X. The P plus region, N well, and P substrate form a PNP transistor, QE. Its collector is external and the emitter connects to the PMOS source. The P substrate links through resistance R to the D line. The NMOS forms an NPN transistor, Q2, with its collector at the N well. Without current, the structure is stable with point X at 0 volts and the external point at VDD. Both transistors are off, creating an open circuit. If signals fluctuate, current may inject into the substrate, raising voltage at point X, turning on Q2, causing an IR drop, lowering external voltage. QE's collector voltage drops below VDD, acting like a PNP transistor. The emitter here is also connected to the power supply, right? It's the source of the PMOS. So the collector is the P substrate, right? So we have this PNP transistor structure. Now let's look further. The P substrate connects to the contact point of the P substrate, and there will also be a resistance R, right? So the P substrate actually connects to point X, and between point X and the final D line, there's a resistance R. Now let's look at the NMOS. This NMOS's collector connects with its substrate and the N-well, forming an NPN transistor. We call this transistor Q2, right? You can see that its collector is at point X, the P substrate X. Its emitter is connected to the collector, so it's also connected to the ground line, and its collector is at the N-well position, which is the external point. So you can see that if an NMOS and a PMOS are very close together, they will form this parasitic structure. Once we have this parasitic structure, let's see what happens if there's no current flowing through the P substrate or the N-well. In that case, the structure is fine, right? If there's no current, then the voltage at point X is 0 volts, and the external point is VDD. For example, if VDD is 3.3 volts, then the external point is 3.3 volts, and point X is 0 volts. Now let's look at Q2. The collector of Q2 is at 0 volts, and the base emitter voltage, VBE, of Q1 should also equal 0 volts. So both transistors are off, right? They are off, so there's no problem. The state between the power supply and ground is an open circuit, which is fine. But the problem arises when the circuit starts to work, like in our larger inverter. When it operates, if the signal fluctuates sharply, it will inject current into the substrate, whether it's the P substrate or the N-well. As we mentioned earlier, once current flows through the substrate, because the base resistance of the substrate isn't 0, it will create a certain voltage. Now, if a current suddenly gets injected at point X, what will happen? The voltage at point X will rise, right? The voltage at point X will increase. After the voltage at point X rises, observe Q2. The collector voltage of Q2 rises while the emitter stays the same, increasing VBE. As VBE rises, Q2 turns on, causing a current at its collector, which flows through E and R1, creating an IR drop issue. This drop causes the external point voltage to decrease. Now consider the QE transistor. Its collector and emitter remain at VDD, but the collector voltage drops below VDD, making QE act like a PNP transistor, leading to VBE conduction. Once it conducts, Q1's collector also has a current, combining with the previous current at point X, increasing the current through R2, causing the voltage at point X to rise again. This rise promotes Q2's conduction, increasing the current through R1, further dropping the external point voltage. This strengthens Q1's conduction, increasing the current through Q1, causing the voltage across R2 to rise again. This process is a positive feedback loop, amplifying the current. The final result is large currents through R1 and R2, creating a pathway from the power supply to D with low equivalent resistance, leading to a short circuit current. If the load is heavy, this current can be large, potentially burning out the load or the chip, causing latch-up. To avoid this, lower R1 and R2 as their conduction condition depends on them. If R1 and R2 equals 0, then it equals 0. So when this VBE conducts, right, once it conducts, a current will also appear at the collector of Q1. This current will combine with the previous current at point X, intensifying the current through R2, which will cause the voltage at point X to rise again, right? This rise will further promote the conduction of Q2, increasing the current through R1. As the current through R1 increases, the external point voltage continues to drop. The external point voltage continues to drop, which strengthens the conduction of Q1, increasing the current through Q1. This will cause the voltage across R2 to rise again, right? So you can see that this process is a positive feedback loop, right? Positive feedback means that the current keeps amplifying. What's the final result? The final result is that the currents through both R1 and R2 will be very large. What does that mean? It means there will be a pathway from our power supply to D, right? The equivalent resistance will be very low. This will lead to a short circuit current from the power supply to D. Once the short circuit current is large, for example, if our load is particularly heavy, then this short circuit current will also be very large, which could potentially burn out our load, or even cause the entire chip to burn out. This is the latch-up problem. So, how do we avoid this issue? There are actually 2 points. The first point is that we can lower R1 and R2. Lowering. R1 and R2 is essentially a condition for their conduction, right? If R1 and R2 equals 0, then it equals 0. So, does that mean we have no activation conditions? Regardless of how conditions are injected, point X remains at 0 and point Y stays at VDD, preventing Q1 and Q2 from turning on. This is the main solution. Another approach is to reduce the gain of Q1 and Q2, which relates to the manufacturing process. However, in layout design, it's crucial to address reducing R1 and R2. In manufacturing, methods like epitaxial techniques can lower R1 and R2's resistivity, reducing substrate resistance and preventing latch-up. Yet large currents can still cause issues. To avoid latch-up, layout designers should add a guard ring. Let's see how to add it. Surround the NMOS with a P substrate contact. In terms of manufacturing, there are some methods to reduce R1 and R2. For instance, using epitaxial techniques can generally lower the resistivity of R1 and R2, making the substrate resistance quite small, which usually prevents latch-up issues. However, if you have a particularly large injected current, even if your current is small, a very large current can still cause it to turn on. So, for us layout designers, to avoid latch-up issues, we need to add something called a guard ring, also known as gathering. Let's take a look at how to add it. For example, on the left, we have an NMOS device, and on the right, we have a PMOS device. How do we add the guard ring? We surround our NMOS with the substrate contact, which is the P substrate contact. We encircle our device with the P substrate. The same goes for the PMOS. We encircle it with N+ in the N well in. This means that all around my device, whether for PMOS or NMOS, it's surrounded by the substrate contact. Of course, you need to be careful that just adding P+ or N+ alone isn't enough. For example, I added P+ here, the yellow part is P+, and on the right side I added N+, which is the dark blue part. But you must remember that simply adding N+ and P+ isn't sufficient. You must also add metal on top. You need to use contacts to evenly distribute it. This means that after you draw a ring of N+ or P+, you also need to draw a ring of metal M1 on top, and then evenly distribute contacts on it. The purpose of this is to ensure that this ring of substrate contacts has reliable potential connections. Because both P+ and N+ have resistance, if you rely solely on them to supply power or ground, they will also create voltage drops, and their contacts aren't very good. So you need to connect this entire ring with M1, ensuring that every position has a reliable connection. For PMOS, it's a reliable power source, and for NMOS, it's a reliable VSS. So after connecting the guard ring, what does it mean? It means that around my device, all the P+ contacts are connected to GND, and all the N+ contacts around the PMOS are connected to VDD. This way, the potential at point Y is stable at VDD, and the potential at point X is VSS. Therefore, you won't encounter latch-up issues. Once there's current injection, it will be immediately absorbed by VSS or VDD, preventing activation at these points, and thus avoiding latch-up issues. This is an important guiding principle. When designing large NMOS and PMOS devices that appear together, always use guard rings to avoid latch-up problems. The fourth point is about electromigration. It is when a very large current flows through metal wires in a conductor, causing burning out or short circuits. For example, we use a household appliance. We plug it into a power strip. You must calculate the power capacity of the strip. If I have an air conditioner that uses 1000 watts and a rice cooker that also uses 1000 watts, totaling 2000 watts, using a 1500 watt strip for both will fail. Integrated circuits face this too. Current flow moves electrons. This flow collides with metal atoms. Low current causes minor collisions. High current moves metal atoms. This causes displacement, vacating atom positions. This creates a gap. Gaps can cause open circuits. High current can clear atoms, causing open circuits. Open circuits cause failure. Alternatively, displaced atoms accumulate, causing extrusion. Extrusion can cause overlap. Large currents cause atom accumulation. Accumulation risks short circuits. This leads to short circuits. Migration causes short or open circuits, leading to failure. Designs must consider electromigration. When current flows, there's electron movement. So what happens with this electron flow? It collides with the metal atoms. When our current is relatively low, these collisions aren't severe, meaning there's no significant impact on the atoms. But once our current density exceeds a certain threshold, meaning the current is very strong, it can cause the metal atoms to move. This movement can lead to what we call displacement, where the position that originally had a metal atom gets knocked out by the high-speed moving electrons. Once that atom is gone, what happens? It creates a gap in the metal, right? If that gap becomes large enough, it effectively turns into an open circuit. So as you can see in the diagram in the lower left corner, when the current is high, it can knock the metal atoms away. Over time, that area can end up with no atoms left, leading to an open circuit. Once there's an open circuit, the circuit will definitely fail, right? That's one possibility. The other possibility is that when the atoms are knocked away, they can move to other positions and accumulate there, which can lead to extrusion. Once extrusion occurs, the metal wire might overlap with adjacent metal wires. For example, if this metal wire is carrying a large current, even if it hasn't burned out yet, the moving atoms can accumulate in a position, meaning the knocked away atoms gather there. The more they pile up, the more likely it is that they will connect with a nearby metal wire, right? This can ultimately lead to a short circuit. So, this migration issue can cause either a short circuit or an open circuit, both of which can lead to circuit failure. Therefore, when we design layouts, we must pay close attention to the issue of electromigration. So, when we are designing the layout, we need to pay very close attention to the issue of electromigration. It's crucial to be aware of the electromigration problem. To manage current density, know the limits of lines and contacts. Metal 1 supports 1 milliamp per micron. A 1 micron line carries 1 milliamp, 2 microns handle 2. Exceeding this causes issues. Metal 2 and higher layers support more due to thickness, with top metal for power lines. Poly handles 0.5 milliamp per micron, not for large currents. Contacts and vias have limits. Contact 1 milliamp via 1.5. Calculate vias needed for current. If M1 and M2 are 5 microns wide, they handle 5 and 7.5 milliamps, enough for 4 milliamps. Connect M1 and M2 with a V1 via. Generally speaking, our metal 1 can handle 1 milliamp per micron. Notice why it's in microns and not in area. It's about width. When we draw metal, it's not a top view, right? For example, if we draw a metal strip, we don't need to consider its thickness because the thickness is fixed. So we only look at the current per unit width. For instance, if it's 1 milliamp per micron and the width is exactly 1 micron, that means this line can carry 1 milliamp of current. If you exceed 1 milliamp, the line might experience issues. If I draw a line that is 2 microns wide, it can handle 2 milliamps. So if you only pass 1 milliamp through it, that should be fine, right? Now, for metal 2, it can handle even more. Generally, the higher up the metal layer, the greater the current density it can handle, because its thickness increases. For example, top metal, M-top, is usually the thickest and can handle a very high current density, which is why top metal is typically used for power lines. Overall, power lines use top metal because of its wider width and higher current carrying capacity, making it a reliable choice for power supply. Now, poly also has current density requirements, which are generally lower, around 0.5 milliamp per micron. Fortunately, we usually don't use poly for carrying large current signals. Besides these interconnect lines, whether it's poly or metal, we also use contacts and vias, right? These two also have current carrying constraints because both contacts and vias are made of metal. For example, when using a tonsil structure for a contact, the current density it can handle is calculated based on how much current a single contact can carry. For instance, a contact can handle 1 milliamp, while a via can handle 1.5 milliamps. So You can calculate how many vias you have to determine how much current you can carry. For example, when jumping from M1 to M2, if the current is particularly high and I calculate the widths of M1 and M2, I find that both widths are sufficient. Let's say I have an M1 and an M2, and I calculated that the current I want to carry is 4 milliamps. I checked the line widths for both M1 and M2 and found no issues. For instance, if I drew M1 as 5 microns and M2 also as 5 microns, according to the table, my 5 micron M1 can handle 5 milliamps, and my 5 micron M2 can handle 7.5 milliamps. So since I'm only passing 4 milliamps through these two metal lines, there should be no problem at all. Both M1 and M2 will be fine, right? Now, to connect M1 and M2, I need to draw a V1, right? I just drew one V and I drew a V1. So, with 7.5 milliamps of current, I can definitely pass 4 milliamps through these two metal lines without any issues. Both M1 and M2 will be fine, right? Now, to connect M1 and M2, I need to draw a V1, right? So I just drew one V and I drew a V1. This is a problem, right? A stomach can handle only 1.5 milliamps, but from M1 to M2, 4 milliamps are needed, affecting this area. It will burn out, right? The stomach faces electromigration issues. We must draw enough of this area. For example, if I draw 4 areas, it will burn out, right? The stomach faces electromigration issues. We must draw enough of this area. If I have 4 areas here, this is adaptable. If I have 4 VAE, those 4 VAA can handle 6 milliamps, right? So if 4 milliamps flow, it should be fine. This means when drawing the layout, we must consider electromigration. 3 or 4 dangers. If I were here, there would be 4 dangers. 4 VAE can handle 6 milliamps. Consider electromigration for metal lines, poly, vias, or contacts to handle large currents. Avoid pushing limits. For 4 milliamps, draw M1 at 4 micrometers. Some chips last 10 years, but without enough margin, they might last only 8. You need to consider whether this metal line, poly, via, or contact can handle such a large current. Avoid pushing limits, e.g. if I need a current of 4 milliamps, I would draw M1 at 4 micrometers as it needs 1 milliamp per micrometer, which is fine, but this pushes limits, reducing reliability. Circuit lifespan may reduce, e.g. some chips are designed for 10 years. Without margin, it may last 8. Long-term edge operation causes issues. Add margin, e.g. for 4 milliamps, draw at 5 micrometers. This adds margin, avoiding reliability issues. But this is pushing the edge, and the reliability isn't very high. The lifespan of the circuit could be reduced. For example, some chips might be designed to work for 10 years without any issues, right? But if you don't have enough margin, it might only work for 8 years, because over a long period of time, operating in this edge state could lead to problems, right? So, we need to add some margin. For example, if I have a current of 4 milliamps, I would draw it at 5 micrometers. At that point, you have some margin, and it won't have reliability issues, right? Well then, when we solve the problem of electromigration, it is obvious that we need to widen the line width, right? So we can see from the example just now. In terms of process, we can use methods like adding copper to aluminum alloy to improve electromigration issues. Copper handles higher current density than aluminum, reducing electromigration. A copper alloy withstands larger currents. However, as layout designers, we can't change materials. In layout design, we adjust. Copper handles more current than aluminum, meaning electromigration in copper is less likely. Copper materials withstand more current. Adding copper to aluminum helps. We can't use this. In layout design, we adjust the width and thickness. For high currents, we need wide, thick metal. Having enough width is straightforward. For 1 milliamp, draw a 2 micrometer line. That should be fine. A 2 micrometer M1 handles 1 milliamp. So for us in our field of layout design, what we can essentially adjust is width and thickness, right? When we need to handle high currents, we need sufficiently wide and thick metal. The concept of having enough width is pretty straightforward, right? For example, if I have a current of 1 milliamp, I would draw a line that is 2 micrometers wide. That should definitely be fine. According to what we discussed earlier, if I have a 2 micrometer wide M1, it can indeed handle 1 milliamp of current. That's the question, right? So, the width is pretty easy to understand, right? If I have a current of 10 milliamps, then I would use 20 micrometers, and that should definitely be fine, right? 20 micrometers should be no problem. So that's the width. But how do we understand the thickness? We've been saying that the thickness of the metal in integrated circuits is fixed, right? Whether it's M1 or M2, the processing thickness is determined by a specific process and is fixed. So how do we address the thickness issue? Well, we can use a parallel approach to solve it. For example, if we want to transmit a current of 10 milliamps, and I want to draw a line that is 12 micrometers wide for M1 to carry this 10 milliamps of current, right? But I find that in my layout space, I can't fit a 12 micrometer line. Due to the layout issues, there's just not enough width for 12 micrometers. So what do? Right? We can use a parallel approach. We don't have to solve this in just one dimension. We can solve it in 3 dimensions, right? I can draw a 6 micrometer M1, and then I can draw another 6 micrometer one on top. I'm R. Isn't that good enough, right? And then what do I do in the middle? I use this V1. Connect them together. Of course, you need to consider the number of vias, right? In that case, when these 2 lines are connected in parallel, it's like your thickness is increased, right? For example, if M1 can originally handle 1 milliamp, it's 1 milliamp per micrometer for M1 and 1.5 milliamps per micrometer for M2. So if you connect them in parallel, can each micrometer handle 2.5 milliamps then? Right. So in that case, you can make the width a bit narrower, right? Through this method, we can think about both thickness and width, or rather, thickness and wisdom. To solve this problem, right? And then there's a third point here that we need to pay very close attention to. What is this third point? It's called the yield effect. The yield effect.
Why is distinguishing this effect important? When transmitting high-frequency signals, we use parallel connections instead of wide contact wires. Parallel wires are preferred for high-frequency, large current signals. You can have different levels of parallelism or the same level, breaking them into strands. We emphasize the same level. In the diagram, when transmitting a fast, large current signal using thick metal poses problems. Due to the yield effect, current concentrates on the surface. The current density is high at the edges and low in the center. This means current is mainly on the metal's surface, underutilizing the center. Even with a large calculated cross-sectional area, using parallel wires is better than wide contact wires. Parallel connections allow different or the same levels of parallelism, breaking into strands. We emphasize the same level. In the diagram, when transmitting a fast, large current signal, what issues arise with thick metal? Due to the yield effect, high-frequency signals concentrate on the surface. Current density is high in red, low in green. In the metal's cross-section, the yield effect causes high edge density, low center density. Thus, the current mainly transmits on the surface, underutilizing the center. Even with a large cross-section, the effective area is small, affecting transmission efficiency. A wide wire may still burn out due to the yield effect. If a wide wire should handle the current but burns out, it's because the current flows on the surface. The yield effect reduces the current density per unit area. Without it, density might be 1 milliamp per micrometer, but with it, it drops to 0.8 or lower. Calculating width based on 1 milliamp per micrometer could cause issues. The current density varies, with red indicating high and green low. At the metal's cross-section, the yield effect causes high current density at the edges and low in the center, meaning current mainly flows on the surface, leaving central areas underutilized. Despite a large calculated cross-section, the effective area is small, affecting signal transmission efficiency. Even wide wires can burn out due to the yield effect as current density per unit area decreases. For instance, without the yield effect, current density might be 1 milliamp per micrometer, but it drops to 0.8 or lower with the effect. Calculating width based on 1 milliamp per micrometer can lead to issues. To address this, we use parallel connections. For example, a 20 micrometer wide metal transmitting high frequency signals is better divided into 10 2 micrometer strands. Or you might have a very large width, but the effective cross-section that you can actually utilize isn't that big. So this kind of situation can affect the efficiency of our wire's signal transmission. Even if the wire is wide enough, there could still be issues like wire burnout because of the yield effect. For instance, if we draw something that is particularly wide, I calculated that this width should be able to handle the current, but it still burns out. Why? Because of the yield effect, right? Even though the width is very large, the current flows mainly on the surface. So once the yield effect occurs, the current density that can be handled per unit area decreases. For example, without the yield effect, I might have a current density of 1 milliamp per micrometer, but once the yield effect kicks in, it could drop to 0.8 milliamps per micrometer or even lower.
If you still calculate your width based on 1 milliamp per micrometer, you might run into problems. So how do we do this? To achieve this, in our work, we often employ a strategy that involves utilizing a parallel approach. For example, consider a scenario where I possess a piece of metal that measures 20 micrometers in width, and I am required to transmit a signal of high frequency. A more effective method would be to divide it into 10 individual strands, each measuring 2 micrometers in width. Each wire is only approximately 2 micrometers, but if I illustrate 10 of them and connect them in parallel, it can help effectively alleviate the changes in current density caused by the yield effect. For high-frequency large currents, we should specifically use this method instead of that one, right? Now, in particular, the fifth issue is, as we know, the problem of metal stress. The issue of metal stress, essentially. So what is this problem, essentially? It refers to when we have very wide metal, or metal with a very large area. Essentially, when we draw this kind of metal, we encounter a problem. Why is that? Because if we draw a very large area of metal, especially when we're working on power lines, the drawing will be quite wide. This is because we need to consider the issue of current density, right? The problem of electromigration. So it might end up being drawn wider. Of course, this is for transmitting power. When it comes to power supply, we draw two pieces. Now you can imagine that such a wide piece of metal is actually a thin, very thin metal sheet, right? It's a thin metal sheet. So, if this thin metal sheet is placed over the silicon during the processing, there will be various temperature changes and different materials involved. The thermal expansion and contraction coefficients of these different materials are not the same. So it will keep experiencing this stretching and compression, right? This stretching and squeezing will have a pulling effect on the metal, which can lead to what? The metal might either get torn apart or develop wrinkles, right? It can develop wrinkles in the metal. So that's why. So this stretching and compression will have a pulling effect on the metal, right? This pulling effect can lead to what? The metal might either get torn apart or develop wrinkles, right? So in this case, it means that the metal will endure a certain amount of stress, which can cause problems like open circuits or short circuits. To avoid these issues, what can we do? Generally speaking, for wider metal, we need to create some what we call slots. Metal will either be torn or wrinkled, right? Metal wrinkles will appear. So what? The metal will endure stress, potentially causing open or short circuits. To prevent this, we can create slots in wider metal, forming a mesh. For example, on the right, I've added elongated holes. The process may have specific design rules for hole size and width. Slots are narrow metal openings forming a mesh. Wide metal needs elongated holes, following design rules for size and density. The design rule check, DRC, verifies these holes. If absent, DRC flags issues like exceeding an 18 micrometer width. In this case, wide metal will look like a metal mesh. I've created a lot of holes. These holes are elongated. Depending on different processes, the method of creating these holes might have specific rules. The design rules say how big and wide these holes should be, as well as how dense they should be. You must follow these specific rules when creating them. When you have this large area of metal, during the design rule check, DRC, it will be checked. If you haven't created any holes, the DRC will alert you there's a problem. Your metal exceeds a certain width, exceeding 18 micrometers. It will tell you, hey, you need to create these slots. There are specific requirements for how dense these slots should be. You need to follow these specific requirements to create them. So, what does this mean? It means that when you have this large area of metal during the design rule check, DRC, it will be checked. For example, if you haven't created any holes, the DRC will alert you that there's a problem, indicating that your metal exceeds a certain width, like 18 micrometers, which is its limit. For example, if it exceeds 18 micrometers, then it will tell you, hey, you need to create these slots. So, the shape of the slots you create has specific requirements. Once the metal is formed into a mesh, what does that mean? It means that it actually provides a certain space for the metal to deform, right? Whether it's stretching or compressing. Because there's space in these areas, it helps relieve the stress on the metal. So, to avoid issues like open circuits and short circuits, we're dealing with the problem of stress. So the last question is about the density issue, the density problem. So what kind of problem is this? Let's take a look. In order to control the consistency of our process, our design rules generally require that the poly and metal achieve certain density requirements. To meet a density requirement, why is that? This brings us to our process, which is chemical mechanical polishing, or CMP. CMP, or chemical mechanical polishing, is widely used in our current integrated circuit processing technology. It's a flattening process that aims to smooth out the surface, regardless of whether it's after the STI is completed or after my metal work is done. There will still be a process to smooth the surface. This smoothing process is called chemical mechanical polishing, or CMP. So we have this. So the whole process is like this. I have a turntable, and underneath it there's a vacuum system that will hold the chip in place. The front side of the chip is flipped over, so the back side is attached to the suction cup, while the front faces downwards. Below that there will be a polishing pad, and on top of the polishing pad we will place the polishing liquid. So we put the polishing liquid on, and then the base will also rotate. The polishing table will rotate as well, with both sides turning in opposite directions. This way it will continuously grind the surface of the chip, right? It will grind the surface of the chip until it's smooth. However, during this polishing process, a problem arises. The hardness of different materials is not the same, right? For example, silicon dioxide is harder than silicon. And then this metal is the softest, so the hardness varies among different materials, and the polishing speed is also different. So the polishing speed is also different. For example, let's say we have a region with a poly layer, like this is my poly region. Generally, what does a poly region look like? It's usually STI, right? So what is STI? STI is silicon dioxide, which is very hard and not easy to polish. However, the poly region, which is the exposed silicon or the active area, is relatively softer compared to STI. So the polishing speed will be faster here, right? So you see, if I have this device, then here, here, in this area, there are quite a few poly regions, while in this area, there are relatively fewer. Or we can take this metal as an example. For instance, if there's a lot of metal here and less metal there, since the metal is relatively soft, when you wear it down, the area with more metal will wear down faster. You know, it will wear down more quickly. So what happens? You get what's called a low characteristic issue. The low characteristic issue refers to dense, which means it has worn down a lot, creating a little dish-like shape here, you know? The dish is indented, and if this gets a bit exaggerated, it could even lead to that area being worn through. It's broken. There are density requirements for metal. Coverage must be uniform with high density, meaning metal should be everywhere for uniform wear. This issue exists for metal, curves, or polishing. Density must be high. Uneven metal distribution is problematic. More metal wears faster, causing thinning and potential failure. This is a density problem. So it really needs to be very uniform, and the density has to be high enough. You can't have some areas where the metal is overly concentrated, while other areas have no metal at all. If that's the case, then, well, the area with more metal will definitely wear down much faster. That will wear down the metal, making it thinner, which can lead to a decrease in our consistency and even potential failure issues. This is all about the density problem. So how do we avoid this density issue? We need to ensure that the density across all layers is relatively uniform. For example, in our metal problem, if I'm designing the layout and there's metal here and metal there, but there's no metal in between, how do we solve this? The manufacturing process will use autofill tools to automatically fill in the gaps. It will calculate and find that the density is insufficient and that there's plenty of space available, so it will use smaller metal blocks to fill in the gaps with metal. By doing this, the density issue gets resolved. However, we need to be cautious. After adding these supplemental blocks, the parasitic environment changes, right? Originally, the distance between these two bases was relatively far apart. If the density is insufficient and there's still plenty of space, then it will use these smaller metal blocks to fill in all the gaps with metal. So with that, the density issue is resolved. However, you need to be careful. After adding these supplemental blocks, the parasitic environment changes, right? Originally, the distance between these two bases was relatively far apart. The parasitic capacitance might be relatively small, but after you add so much metal, there will be a lot of coupling capacitance between this metal and the metal of your normal wires. This makes the entire absorption environment more complex. right? So his parasitism might change. So once the parasitic capacitance changes, it can affect your circuit characteristics, right? Therefore, you really need to pay attention to this capacitance, especially in critical areas. It's best if you fill it in yourself. You should fill it in yourself and not use those tools for filling. Because what are tools? Tools are automation, right? Automation doesn't take into account the specifics. It just fills in wherever it meets the conditions. But in some areas, it might affect the circuit characteristics. So, for designers, you really need to be careful about these positions. You have to pay enough attention. For example, you need to consider how to fill in these areas. After filling them in, you must conduct thorough post-simulation to verify whether the added metal will affect your circuit's performance. You definitely shouldn't think that just because you've added metal and ensured good consistency, the circuit characteristics won't be affected. That would be a mistake. Consider how to add this position. After adding, you must do enough. What is this? Post-simulation. Make sure to conduct thorough post-simulation to verify whether the added metal will affect your circuit's performance. You mustn't think that just because you've added metal and ensured good consistency, the circuit characteristics won't be affected. That would be a mistake. All right, so that's all for this video.